All right, let's talk about a part of math that has, let's be honest, a really bad branding problem. Complex numbers. I mean, the name itself sounds tough, and it's all built around something called an imaginary number. But what if I told you these numbers are not only way simpler than they sound, but they're actually the secret language behind, well, pretty much everything, from your phone signal to quantum physics. Let's get into it.
So, to really get why we even need complex numbers, we have to go back in time and look at a question that was a total dead end for mathematicians. A question that just seemed impossible.
I mean, think about it for a second. You take a positive number and multiply it by itself, you get a positive, right? You take a negative number and multiply it by itself, you still get a positive number. So how in the world could you ever get -1? On that normal number line we all learned about, there's just no answer. It's a wall.
Or is it? You see, faced with this wall, mathematicians did something kind of gutsy. They said, okay, if the number we need doesn't exist, let's just invent it. And so they created the imaginary unit, which we call I. It has one simple rule. I times I equals -1. And that one simple move didn't break math. It blew it wide open into a whole new dimension.
Okay, so we've got this powerful new tool, I. How do we actually use it to build one of these new kinds of numbers? Let's take a look at the blueprint. And here you have it. This is the whole anatomy. Every complex number looks just like this. It's a mix of two parts, a real part, A, that's just a regular old number, and then an imaginary part, B, that's attached to our new friend, I. That's the entire design. Simple, right?
So if you see a number like 3 plus 4i, it's super easy to break down. The real part is just 3. The imaginary part is 4. It's just a single number that happens to have two distinct pieces of information packed inside it.
And this is where it gets really cool, because this isn't just some abstract idea. That mathematical notion, 3 plus 4i, translates directly into a single, clean command in a language like Python. This concept is so useful, it's literally built into the tools we use every day.
Now, adding and multiplying these things is pretty intuitive, but division has this really clever little trick. To get that pesky I out of the bottom of a fraction, you use something called its conjugate. And all that means is you just flip the sign on the imaginary part. You multiply the top and bottom by that conjugate, and like magic, the imaginary stuff on the bottom just cancels itself out. It's a beautiful piece of mathematical cleanup.
We all know the classic number line, right? Goes left for negative, right for positive. It's a flat, one-dimensional world. All the real numbers live there.
But see, a complex number can't live on that single line. It's got two parts, so it needs two directions. We keep our regular number line for the real part, and we add a whole new axis, a vertical one, for the imaginary part. And just like that, our line becomes a plane. Every single complex number has its own unique address here.
So once you see that number as a dot on this map, you can ask a really simple question. How far is that dot from the center, from 0? Well, that distance has a name. It's called the modulus. It's just the straight line length from the origin out to your number.
So how do you find that length? Well, the formula is just the Pythagorean theorem. Yeah, the same a squared plus b squared equals c squared from geometry class. But what's awesome is how code just handles it. In Python, you don't even type the formula. You just ask for the absolute value, abs of z, and bam, it gives you the length. Okay, so we can describe any point on this plane with its real and imaginary coordinates, right? Like go over this much, go up that much. But that's not the only way to give directions. There's another way, a really powerful way.
And this is called polar form. Instead of saying, go 3 over and 4 up, you can give directions a different way. You can say, turn to face this angle, and now walk this distance. The distance, r, is just the modulus we already found, and the direction is just an angle, theta. It's the same spot, just described in a new language.
This all leads us to what is, no joke, one of the most beautiful and profound equations in all of math, Euler's formula. What's so amazing about it? It shows this totally unexpected, hidden connection between the number e, which is all about growth, and the functions for sine and cosine, which are all about circles and rotation. And the imaginary number I is the bridge that connects them. It's wild.
So the big takeaway from that amazing formula is this. It lets us write any complex number in this incredibly elegant and compact way. All the information, the distance r and the angle theta, gets packed into one simple little term. And as you're about to see, this changes the game completely.
So let's end on this thought. We started this whole thing by inventing a new dimension just to solve one impossible little equation. But in doing that, we accidentally stumbled upon an essential tool for designing electrical circuits, for processing digital signals, for understanding the weirdness of quantum mechanics, and even for creating beautiful fractal art. It just makes you wonder, right? What other impossible problems are out there just waiting for us to look at them from a new dimension?